It's hard to exaggerate the enthusiasm that workers in the field greeted the idea of a computational theory of the mind. I remember the enthusiasm of those early days. Some of the most famous figures in the field, many of them had achieved great intellectual distinction in other fields already, were saying such things as Herb Simon and Alan Newell said in their what they called a physical symbol system hypothesis. The idea was that we have now discovered that the mind is a symbol system. It's a system that operates on symbols, and it doesn't matter what medium it's in. It could be in brains, it could be in silicon chips, it could be in vacuum tubes, it could be literally in anything that was rich enough and stable enough to sustain the symbol manipulations which were the essential component of thinking. So great was the enthusiasm that Simon and Newell compared themselves to the greatest scientific discoverers of history. When perhaps with something less than total modesty, they said their discovery of the physical symbol system hypothesis was comparable to the germ theory of disease, the DNA theory of genetic inheritance, the atomic theory of matter, and the tectonic plate theory of geology. They had other examples, but those are the ones that spring immediately to mind. Now, you wonder, what is going on? I mean, if somebody's comparing their, I think, rather doubtful view to the atomic theory of matter or to the germ theory of disease or to the greatest scientific discoveries of history, they must think they've got some real substance to this. So before subjecting this to criticism, I want to tell you some of its intellectual foundations. I want to give you some idea of the intellectual underpinnings of the computational theory of the mind. I have to mention in passing that Simon and Newell were not the most immodest or the most exaggerated in their enthusiasm. I guess my favorite was Marvin Minsky of MIT, who said, "We're now making computers that are so smart that we'll be lucky if they're willing to keep us around the house as household pets." And I have heard Marvin say that, so I know that's a correct quote. He was quoted in the New York Times. I find this hard to believe, but anyway, the New York Times quoted, well, maybe it isn't so hard to believe. He said that since we're programmed into this rather stupid wetware that's going to decay and die and all kinds of terrible things happen to it, what we should really do is get our minds reprogrammed onto some decent hardware where we could have something like immortality. We could go on living as VAX computers or maybe Cray supercomputers after this dumb wetware that we were born with is fully decayed. Anyway, I want to give you the idea that a lot of people accepted this. It was well funded. There were lots of research grants and still are, though they're more doubtful now than they were in the past. And it wasn't just out of the blue. There was a historical development that I tried to explain in the last lecture, but there were also serious intellectual underpinnings for the idea that we might discover the secret of our own existence, the secret of our own nature, by seeing ourselves as digital computers and our minds as computer programs programmed into the wetware or the implementation mechanism, whatever it is, in our brains. There are 5 ideas that I think are essential to understanding this. The first idea is the notion of a Turing machine. That's named after Alan Turing, T-U-R-I-N-G, the inventor of these ideas. Turing was one of a group of brilliant logicians and mathematicians who made a large number of important discoveries, really as early as the 1930s, but continuing right on into the 50s. The idea of a Turing machine is an abstract mathematical idea of how problems can be solved by implementing them in a binomial system, in a system with only 2 symbols, 0 and 1. And a Turing machine is ludicrously simple in its basic operations. A Turing machine can perform exactly 4 operations. It can erase a 0 and print a 1. It can erase a 1 and print a 0. It can move its head 1 step to the left. It can move its head or its scanner. It has a tape, and it can move it 1 step to the right. So it can move left or right. It can erase symbols and print symbols. It's a purely abstract mathematical idea. It's really a mistake to call it a Turing machine. It ought to be called a Turing program or a Turing abstract idea. However, the amazing thing about this abstract idea is you can actually put Turing programs on real machines, on real electronic machines. And though, as I said, there aren't any Turing machines in real life and can't be because, for example, they have an infinite amount of tape. And in real life, there aren't any machines that have an infinite tape. And they are purely abstract. Nonetheless, and this is the important thought, for practical purposes, the ordinary computer that you buy in a store is a Turing machine. It performs these operations, though not in the way that I described. It doesn't have an actual tape, but it performs something that's functionally equivalent to that by manipulating symbols. With binary symbols, zeros and ones, you can do an enormous amount of intellectual operations. Now, what has happened with the development of the technology is we can now make Turing machines that manipulate these symbols at a very rapid rate, like several million per second. So you've got millions of these symbolic operations going on in ordinary household computers. If Turing were alive today, it would take his breath away to see what you can buy for a couple of $1,000s in any computer store, because it is a level of computing power that far exceeded anything imaginable at the time he developed the idea of a Turing machine. Okay, that's the first notion, the idea that there are Turing machines and they perform these complex operations, such as complex mathematical operations, by breaking them down into a series of simple operations that involve only the manipulation of zeros and ones. It's an amazing and a powerful idea. The second idea that we need is the idea of an algorithm. And the idea of an algorithm is the idea of a procedure that will solve a problem by going through a precisely statable series of steps. A finite series of steps will solve a problem. So, for example, if you learn to do addition or long division, there is an algorithm for performing those. You do a precisely statable series of steps, and you take in an input, a bunch of numbers, and you get an output. You get a result which is precisely determined by following the algorithm. Now, the importance of the algorithm for our present discussion is that a computer program is an algorithm. What a computer program does is give the machine a set of rules for manipulating those symbols. Now, let's talk about that a second. I said the machine manipulates symbols, but it does that according to a set of rules. And those rules always have the same form. They always say, under condition C, perform act A. They're of the form, if C, then A. So if you have a symbol 0 in this slot, erase that symbol and print a 1 and move 1 square to the left. That would be a typical rule that a computer would follow. Now, a set of those rules is called a computer program, and computer programs are algorithms in the sense that the computer doesn't worry about ambiguities or how to think its way out of a complex, muddly, ambiguous situation. It does what it's told. It takes in an input, and it has a computer program that tells it exactly what to do with that input, and it prints out an output, and that sequence of steps is called a program, or alternatively, an algorithm. Now, why is that important? Well, there was a very important idea that also grew out about this time and was arrived at independently by a bunch of thinkers, but it's usually called Church's thesis, after the famous mathematical logician Alonzo Church. It was arrived at independently by other people, among them Turing and I think also Post, but it's usually called the Church's thesis or the Church-Turing thesis. Now, again, we're putting all these ideas together, and the idea now is any algorithm at all can be run on a Turing machine. Any problem at all that you can solve with a series of precisely statable steps can be solved on a computer, can be done computationally, can be solved on a Turing machine. In slightly more mathematical jargon, any computable function, that is, any mathematical function where there's a definite solution that you can arrive at by going through a series of steps, that can be programmed onto a computer. A computer can do anything that any algorithm can do. That's a very exciting idea. This is called Church's thesis because it's not actually proven as a theorem, since the notion of an algorithm is not all that well defined. I just give you an intuitive idea of what an algorithm is. But nonetheless, it's a very powerful idea, and it's actually one of the most powerful ideas in the 20th century, is the idea that this simple device that has only a binary set of symbols, zeros and ones, can solve any problem that can be solved algorithmically, any problem at all that can be done in a precisely specifiable finite series of steps. Now, there's one further idea. This is our fourth idea, and that was also arrived at by Turing, and it's usually called Turing's theorem. And the idea there is, and Turing actually proved this as a theorem, that if you've got these Turing machines, which are these devices that manipulate zeros and ones and implement these programs that are algorithms, then there is a universal Turing machine that can simulate the behavior of any other Turing machine. Now, let me explain that idea a little bit. Again, these are abstract mathematical ideas, but the idea is basically very simple. We understand what a Turing machine is, we understand what an algorithm is, and we see that that's important because we see that any problem you can solve algorithmically, anything at all, you can do on a Turing machine. But now it turns out that there is a universal Turing machine such that that Turing machine can simulate the behavior of any other Turing machine. Any Turing machine at all can be exactly duplicated on a universal Turing machine. Now, once again, when we use the word machine, that's misleading. I don't want you to get the idea, I want to go into a shop and buy a universal Turing machine, because these are abstract ideas. It should really be called a program and not a machine. But the importance of it is that you can implement it. That is to say, for practical purposes, the computer that you buy is a universal Turing machine, because theoretically, at least, I mean, you wouldn't actually go through the trouble to do this, it can take any program. Any Turing machine program can be run on an ordinary household computer. That's what a general purpose computer is, as opposed to specifically dedicated computers. Okay, so those are four basic theoretical ideas. The idea of a Turing machine, an algorithm, of Church's thesis and Turing's theorem. But now, in addition to them, there was a fifth notion, and this is not a theoretical idea, but it's a practical proposal, and it's called the Turing test. How much of this is due to Alan Turing? It's really quite amazing. Turing proposed the following. If we're going to design programs to simulate human intelligence, we need a test. We need a test for when we've succeeded. We need some way of telling when are you winning in this game and when are you losing. And Turing proposed the following. If you had in one room a human being giving answers to questions, and in another room a machine giving answers to questions, and you had an expert in the middle passing in questions to each of these two rooms and getting back the answers, if the expert couldn't tell the difference between the machine answer and the human answer, then you'd have to say that the machine was as intelligent as the human. If the machine can behave in a way that the expert can't distinguish from human behavior, then the machine has human-level intelligence. So, for example, if you were making a program to simulate the behavior of a Chinese speaker, and you got a machine that could pass the Turing test for the understanding of Chinese, you would have to say the machine understands Chinese. The idea is you'd have a Chinese expert giving questions to a Chinese person in one room that he can't see and to a machine in another room that he can't see. And if the expert gets back these answers and the machine's answers are as good as the human answers, then you'd have to say the machine now literally understands Chinese. It doesn't just behave as if it understood Chinese or simulate the behavior of understanding Chinese. It literally understands, because that's what the Turing test tests. It tests whether or not something literally understands. Now, those 5 ideas, the idea of an implemented algorithm or program running on a Turing machine, implemented in a Turing machine, a machine which is such that it can implement any algorithm, and the idea of a universal Turing machine that can simulate the behavior of any other Turing machine, and the idea of a test, a valid, objective test that'll tell the difference between success and failure, between real understanding and fake understanding, the idea of a scientific way of finding out when we have created machine intelligence. All of those led to an idea, the very statement of which still sends shivers up and down my spine. It's this: maybe the brain is a universal Turing machine. That is, maybe what we've got in the human brain is inside our skulls is we got a Turing machine, not a mathematical, not an abstract one, because of course there are irrelevant considerations like the fact that we're all going to die and we have finite memories. We can't have an infinite amount of tape. But if you subtract this kind of irrelevant stuff, like the fact that it's made of wet stuff and we go to sleep at night and get drunk and otherwise muck up the program, if you subtract that, it looks like at last we've made it. We've discovered the answer to our questions. The brain is a digital computer. It is, in fact, a specific kind of a computer. It's a kind that can implement a Turing program, and that's what a digital computer does. It implements these algorithmic programs. And so now, furthermore, not only have we got a theory that intelligence is a matter of implementing computer programs, but we've got an objective test. And the test tells us if you can design a program that will pass the Turing test, then you have actually created human-level intelligence. You have created a mind. And then this had another feature which was immensely attractive, and that feature was there's a research project. There's a research project that a whole lot of people can do. You have a bunch of people who program the computers so that they can pass the Turing test. But then also there's real work for the psychologists, because what the psychologists do is try to figure out whether or not the way that the machine solves the problem is the same as the way that human beings solve the problem. And that was done by psychologists with such things as reaction time experiments, where you study whether or not the reaction time that the human being has in recognizing faces, or the reaction time in doing remembering numbers in sequences of random numbers, whether or not that is parallel to the different processing times that computer programs take to carry out various cognitive tasks. Okay, so far so good. Now, but you might say, but look, there is something fishy about this, because Turing machines can be run in anything. We happen to run ours now in silicon chips, but there's no essential connection between computers and silicon chips. It just happens that that's the best technology at present. No doubt it will be superseded. Prior to that, we had transistors, and prior to that, we had vacuum tubes. But you can also use an abacus, or you can have a bunch of men sitting on high stools wearing green eye shades, calculating, adding up columns of figures. All of those systems are Turing machines, because all of them are implementing programs. They're all carrying out algorithms. Now, this is another exciting idea. It doesn't matter what the physical system is, whether it's a brain or a bunch of transistors. One writer says, look, you can implement a Turing machine program with a bunch of pigeons pecking. And another author, Ned Block, said, You could have a computer program that is entirely uses mice and cats and cheese. And I forget how it goes, but the mice is released and that's a 0, and then the cat jumps on the mouse and that's a 1. It doesn't matter. Anything goes, provided only that it has this level of symbolic description. Now, this phenomenon whereby anything stable enough and rich enough to carry the program is a computer, that's got a name. It's a very important name. We're going to see more about it later. It's called multiple realizability. The computer program is realizable in a large number of different forms. In fact, it's indefinitely realizable, provided that any realization, as I said before, has to be stable enough to carry the program and rich enough to carry the program. But anything that can carry a program is a computer. It doesn't matter what it's made of or how fast it works. It just, can it implement the program? Can it carry out the steps in the program? Okay, that's the basic idea, and I've done my best to try to make it sound appealing. And if I didn't make that sound at all appealing, then I haven't done my job as an intellectual of the 20th century, because those ideas are among the most powerful and exciting of the late 20th century. And now I'm going to refute it. I think the whole thing is a massive error, and it's the beautiful thing in this field. The computational theory of the mind, strong AI, has two wonderful features that almost none of those other theories that I mentioned have. First of all, you can state it simply. The mind is a computer program. The brain is a computer hardware. That's just very simple, and we're all familiar enough with computers that we have some idea what that means. And furthermore, not only can you state it simply, you can refute it in a few minutes. I mean, it takes 5 minutes to state the refutation, and I'm now going to do it. Somebody can time me if they like. Here's how the refutation goes. When anybody gives you a theory of the mind, always ask yourself, what would it be like for me? What would it be like if my mind actually works the way these guys say that all minds work? I mean, that's how I tried behaviorism. If somebody says there's nothing to your mind except your behavior, you know that's false. Because you know in your own case, when you feel a pain, there's a difference between behaving as if you feel a pain and actually feeling a pain, right? It's obvious. I think it's obvious for any theory of the mind that the first test is always try it on yourself. And there's a deep reason for that, namely, our minds have a first-person existence. Our mental states only exist as experienced by individual human beings. So any theory of the mind has got to pass the me test. It's got to get past me and my experiences. Well, let's try it out with strong AI. Let's suppose that somebody designs a program which will enable a computer to pass the Turing test in some domain that I don't understand. Then what I imagine is that I carry out the steps in that program. Now, I don't understand Chinese. I can't understand a word of Chinese. I can't even tell Chinese writing from Japanese writing. So if you can understand Chinese, take a different example. But I'd like each person hearing this to think of this in their own case. In his or her own case, how would it be? And here's how I think of it for me. Let's suppose that I am locked in a room. I can't see outside the room. I'm locked in a room, and in this room there are a bunch of boxes full of symbols. These are Chinese symbols. Now, I don't know what these symbols mean because I don't know any Chinese. I don't know a word of Chinese. And let's suppose also that I have a set of rules written in English for manipulating the symbols. And the rules say things like, go into box number 1 and take out a squiggle squiggle sign, and then go to box number 2 and match the squiggle squiggle sign next to the squoggle squoggle sign. And you can imagine any Chinese symbols you like here. Now, just to look ahead a bit, rules like that have a name. Those are called computational rules. They tell you, under condition C, perform act A. They're the kind of things that Turing machines do. I put it in terms of Chinese symbols instead of zeros and ones, but it all comes out the same in the end. Okay, so there I am. I'm locked in a room, and I got these boxes of Chinese symbols, and I got a rule book written in English for shuffling the Chinese symbols. Now imagine also that outside the room, there are a bunch of people who pass me little packets of Chinese symbols. And when I get these little packets, I look up what I'm supposed to do. And it says match them next to that symbol and match them next to that symbol. And eventually I go through all the steps, and it says give them back a symbol that has this shape. Okay? So symbols come in, I shuffle them according to the rules, and I give back symbols. That's all that's going on. I don't understand a word of this. You can think of me as motivated by the fact that they're paying me well, or I get free beer, or whatever, but I'm there knowing nothing. All I do is shuffle symbols. Okay, now let's suppose that unknown to me, the people on the outside of the room call the rule book according to which I shuffle the symbols. They call that the computer program. And those boxes of Chinese symbols, that's called the database. And the little bunches of symbols they give into me, they call questions. And the bunches of symbols I give back to them by following the program and using the database, they call answers to the questions. And let's suppose also that I get so good at answering the questions that after a while, my answers are indistinguishable from those of a native Chinese speaker. I pass the Turing test for understanding Chinese. Everybody got the picture? I mean, they're asking me questions. I get a meaningless squiggle. Doesn't mean anything to me. Unknown to me, the question is, what's the longest river in China? And I give back an answer that says, I don't know, could be the Yangtze, could be the Yellow River, one or the other, which is probably, for me, the correct answer. But I know none of that. I don't know what any of these mean. All I know is I've got Chinese symbols that look meaningless to me, and I shuffle them around and give back other Chinese symbols until eventually they get so good at writing the program, and I get so good at shuffling the symbols, my answers are indistinguishable from the answers of a native Chinese speaker. I'm passing the Turing test for understanding Chinese. Okay, now here's the point. Here's the punchline of this little parable. I don't understand a word of Chinese. And there's no way I could ever come to understand Chinese the way we describe this, because I don't know what any of these symbols mean. They're all just meaningless symbols. But now, and this is the moral of that punchline, if I don't understand Chinese on the basis of manipulating symbols, that is to say, on the basis of implementing a computer program for understanding Chinese, then neither does any other digital computer understand Chinese, because no digital computer has anything I don't have. That is what a computer is. Remember what a Turing machine is. A Turing machine is a device that manipulates symbols. It pays no attention to the meanings of the symbols because it doesn't need to. It operates on the symbols entirely in virtue of their form, entirely in virtue of their shape. So the basic moral of the story, I mean the bottom line of this particular story, is that you couldn't possibly give a machine understanding by giving it a computer program, because on the basis of the computer program for understanding Chinese, which I took as an example, you don't understand anything. You understand nothing of the Chinese. The only thing I understood in the parable were that I had English words in which the program was written. That's incidental, but I don't understand any Chinese on the basis of implementing a Chinese understanding program. And if I don't do that, then neither does any other digital computer, because no computer has anything I don't have. And when I understand English, I can't be doing it solely on the basis of a computer program, because we've just seen that a computer program is inadequate. Now, what's going on in this argument? Let's stop and think about it a little bit. This argument occurred to me 15, 16 years ago, and under odd circumstances. I'll tell you a little bit about them. In the early days of cognitive science, the Sloan Foundation generously funded cognitive scientists to go around the country and give lectures. Since we were financed by the Sloan Foundation, we were called Sloan Rangers, an obvious label. And I was going to be a Sloan Ranger going to Yale to lecture to the Artificial Intelligence Lab about their research project. And I didn't know anything about artificial intelligence. I could barely spell it. But I bought a book written by the people there, and I read it on the airplane, and they were designing these story understanding programs. And the idea was that they had these wonderful stories. And here's a typical story. A guy goes into a restaurant and orders a hamburger, and they bring him the hamburger and it's burned. And then the guy leaves the restaurant and goes away. And now they program all of that into a computer. And then you ask the computer, did the guy eat the hamburger? And they're very proud of the fact at Yale that the computer will answer, no, the guy didn't eat the hamburger. Now, do you remember, I didn't say in the story. I just said the guy left the restaurant and went away. I didn't say whether or not he ate it, but the computer can make an inference. So they think, well, that proves the computer understands the story because it can pass the Turing test. It can make the kind of inferences that humans could make. And it seemed to me at the time, and still seemed to me, that doesn't prove anything. Because I could be doing all of that in Chinese, and I don't understand anything. And if I don't understand anything, neither does the computer. I behave as if I understood. That's the Turing test. But what this shows is the Turing test is no good, because it can't distinguish real understanding from behaving as if you understood. Well, I was a little bit depressed when I thought of that, because I thought, well, first of all, they must have thought of this already. It would occur to anybody who heard about these computer programs. And secondly, I thought I'm supposed to give a whole week of lectures in Yale, and that's only going to take 5 minutes. They must surely have an answer to that. Well, it turned out they didn't have an answer to that. Everybody was convinced I was wrong, but no two people agreed on exactly why I was wrong. And little did I know, I'm not sure it was such a good idea there on United Airlines at 30,000 feet thinking about the Chinese room while I was waiting for them to bring me dinner. In the past 15 years, there must have been 200 published attacks on that little argument, the Chinese room argument. And I'm going to talk about some of those attacks later. But let's explore some of the implications of this. I said, just implementing the computer program by itself is not enough for understanding anything. And I showed this by giving an example where I implement a computer program for understanding Chinese, but don't understand any Chinese. But now what's the difference between understanding English, which I do understand, and carrying out a program for understanding Chinese, which I don't understand? Let's go back to the Chinese room. There I am locked in the room, and I get these questions in Chinese, and I give back answers in Chinese, and I don't understand any of it. Suppose they also ask me questions in English. They ask me questions in English. What's the longest river in the United States? And I say, well, it's the Mississippi, but I like to think of it as the Missouri Mississippi because it's one big long river with two names. Now, from the outside, my answers to questions in English look no different from my answers to questions in Chinese. In English and in Chinese, I am passing the Turing test. From the outside, it looks exactly the same. But from the inside, there's an obvious difference. Well, what's the difference? I don't see any reason why we shouldn't accept the common sense answer. The common sense answer is, in English, I know what these words mean. That is, I have not just meaningless formal symbols, which is what a computer has, but I actually have an understanding of the formal symbols. I have more than just the symbols. I've got a semantics. I have meanings that I can attach to the symbols. That's the difference. All right, but now that leads to the next question. Well, why couldn't we give that to the computer? Why couldn't we program the computer with the meanings as well as with the symbols? After all, if I know the meanings of English symbols, why couldn't we program in the computer not just the symbols, but their meanings as well? But now to answer that, remember what the definition of a Turing machine was. It's a device that manipulates symbols, uninterpreted formal symbols. That's not the weakness of the Turing machine. That's not a weakness of a computer. That's the source of its power. It's powerful precisely because it doesn't have to know what any of that stuff means. It just has zeros and ones or Chinese symbols or yeses and nos or X and Ys. Any system at all that can be precisely formally defined, any system at all that can undergo a set of state transitions in the operation of the computer, any system at all of that type is a computer. And any system that can carry those state transitions will be implementing a computer program. So there isn't any way we could program a computer with meanings in addition to symbols, because by definition of the computer, what the computer does is implement symbols. And to repeat, that's the power of the computer. The power of the computer comes precisely from the fact that it doesn't have to know what any of this stuff means. It doesn't have to be conscious. All it has to do is be able to manipulate the symbols, to carry out very rapidly a series of symbol manipulations. Okay, I think that argument is decisive, but I have to tell you that my view is not universally shared, and I'm going to spend some time explaining some of the most powerful objections to it. Now, frankly, I am puzzled by the depth of the hostility that this little argument, which is not very ambitious, it's rather simple. Any beginner can understand the argument. All it says is, look, understanding can't be just carrying out a computer program, because I can carry out the computer program for something I don't understand, and I still won't understand it. But the fact that there was so much hostility to this argument, that to this day I get so much anger about it, suggests to me that it's almost like a religion, the idea that the solution to our problems is essentially a computational solution. It almost has the status of religious faith, and people feel deeply challenged if you say, no, look, there's a fundamental error at the core of this. Let me tell you some of the answers that were proposed to this. When I first presented this argument, the most common answer I got, I found very puzzling, but it was this. There you are in the room, and you are manipulating the Chinese symbols, but remember, you are not alone, because you admitted you had boxes of symbols. You probably had a scratch paper on which to write down the instructions. You had a rule book. There was a whole room. There was a window to the room in which questions came in, and another slot in which answers went out. And it isn't you who understands in the room. It's the whole system that understands. It isn't the individual who understands. It is this entire computer system. In fact, you, a rather minor feature of the system, here comes a magic word, you are just the central processing unit. Nobody ever thought a CPU could understand anything. It isn't the CPU, it's the whole computer system that understands. Now, when I first heard this, I was in a debate, and I said to the guy who presented it, I said, you mean the room understands Chinese? And the guy said, yes, the room understands Chinese. Well, I admire courage. I think it's terrific that people have the nerve of their preposterous views. But I have to tell you, I don't think that's going to help us much to say the room understands Chinese. But if you like that answer, then think of it the following. Just vary the experiment a little bit. Instead of me in the Chinese room with all my symbols and my rule book, imagine that we get rid of the room and I memorize the symbols and memorize the contents of the rule book and carry out all the operations in my head. And if you like, I can work in the middle of an open field. So there isn't anything in the room that isn't in me. Of course, this is science fiction. We couldn't do it in real life, but then we can't actually program computers to understand to simulate understanding Chinese in real life either. So as a science fiction example, we can imagine that I work alone in the middle of the field. Now, I gave this a name, this reply, the reply that says it's the whole system that understands Chinese. I call it the systems reply. And the answer to the systems reply, I think, is very simple. Let me be the whole system. And if I am the entire system, and I don't understand Chinese in virtue of implementing the computer program, then neither does the system, because there's nothing in the system that isn't in me. Well, why not? What's going on? What are we lacking? Well, to repeat, and this is the key point I want to keep emphasizing, what is missing is any content. The formal symbols by themselves have no content, no meaning. They are, to use the linguist jargon here, purely syntactical. That is, we're talking about formal symbols and formal symbol manipulations. Now, if we keep that in mind, that it's the formal structure of the symbols which is both the power and the limitation of the computer. It's the power of the computer because you can implement the same program in an indefinite range of hardwares, and one and the same hardware can implement an indefinite range of programs. Then we see that the underlying insight behind the Chinese room was one that doesn't emerge obviously in the example itself, but it is this. The formal syntax of the computer program, the structure of the program as a purely formal set of symbol manipulations, can't by itself be sufficient for the essential feature of the human mind, namely our thoughts have contents. I don't just think in meaningless symbols. I think in English words. I think in images and pictures. I have a series of mental contents that I associate with the words. So if I think the sequence of words, my income tax will be handed in late this year, those are not just meaningless symbols going through my mind. On the contrary, they have a very deep meaning for me. They send a shudder down my spine every time I think of those. But not because I got a bunch of zeros and ones, but rather because I have English words whose meaning I know. And the computer's power derives precisely from the fact that it knows nothing of meanings or anything else. The power of the digital computer is precisely what makes it inappropriate as a model for the human mind. And in one sentence, the computer program has only empty symbols. The human mind has contents. The only interest that the human mind has in symbols is that it can attach contents to them, and that's true of computer symbols as well. Well, I would like to say that's the end of the story about the computational theory of the mind. Unfortunately, that is the entering wedge into a whole series of philosophical issues that the Chinese room raises, and we will consider those in the next lecture.